Hello everyone, how you doing? I just wanted to record another video um, that covers TensorFlow Playground a little bit better. For some reason, the TensorFlow Playground portion of the video and the lab from the prior lecture just didn't record. It was real choppy and didn't show it the way I wanted to show it. So I'm re-recording this again so that you've got a clearer, cleaner understanding of what it is I'm trying to go for. So this is TensorFlow Playground. So what I'm showing here, and I wanted to show, is a couple things. One is the activation function, as well as the architectural view of a neural network in motion, and also to emphasize that one. The performance of a deep learning architecture is not predicated on the activation function alone or the architecture of the hidden layers, but it's actually both. So it's the activation function as well as the way that the hidden layers are constructed. So this is a great view of how TensorFlow can show you how that works in tangent. So actually what I've got here is when you pull TensorFlow up, you're going to have two different types of problem types. There's classification and regression. Regression is for prediction. Classification, of course, is for categorization or prediction on categories. In this case, we'll stick to classification just to kind of keep it simplified. And over on the left-hand side of your screen over here, you've got three different target data types that you're going to be creating a neural network to classify. So this is a circle. This one is actually a data set that has four squares that are represented by two colored dots, and they're in different opposing areas. So classification task in this case for machine learning, in our case a deep learning neural network, we're actually going to try to create a neural net to classify the outer orange ring and then the inner blue ring. And then in this case, we'll create another neural network to classify the different clustering that's occurring and be able to differentiate the dots just based on their coloring. There's a more complicated one, which is the spiral. And that's one that I want you to do on your time and to determine what activation function works best to classify this spiral, because that spiral actually is it's a very complicated task. Even though the human brain can discern it very quickly, it's actually a very complicated task in terms of getting a machine to recognize that. So let's start with the first one here, the circle where we've got a blue inner dots and then outer orange dots. So I'm going to fire this up with first a linear activation function, and I'm going to have two hidden layers for my neural network. So I've got two inputs, and then I have four neurons on the first hidden layer, and then two neurons on the second hidden layer. So I'm going to do a classification exercise just using, it's essentially a linear algebra. So this is nothing more than just y equals to mx plus b. We're just putting it on steroids by using the linear activation function that is y equals mx plus b added to each one of the neurons. So that's what we're doing with regard to a neural network. And we're going to push play and we're going to see what happens. I suspect that because this is a radial pattern, that a linear activation function isn't going to work really well in this case, at least not based on the input features we've provided it. And as we can see, not much is happening even after 100 couple epochs. We don't see that much going on. So I'm going to stop it, and then I'm going to change it to a sigmoid. And a sigmoid function, I don't believe is going to perform any better versus the linear, just based on the way the math operates with a sigmoid function. I just don't think we're going to see anything happening, and we're not. Now I'm going to switch it to a hyperbolic tangent. And a hyperbolic tangent actually has a lot more capability mathematically to plot different varying shapes or find different shapes. So I have a sneaky suspicion that this is going to work for us. We'll let it do its work. And slowly, you can see it's slowly starting to, and then there we go. So in about 50-ish epochs, we get actually it's a perfect classification of blue in the middle and then orange on the outside. So it was able to classify that pretty quickly. Let's look at a rectified linear unit and see how that operates. These can be pretty good. That's not bad either. It's probably not as clear cut as the hyperbolic tangent, but the rectified linear unit does an excellent job as well. So we can see here in example 1 for the circle target classifier that we're going after. We can see that of the 4 activation functions, rectified linear unit and hyperbolic tangent work the best. So let's go to the next one. And then in this case, we're going to do the same thing, but I'm going to play with this a little bit. I'm going to go from a linear, and then I'm going to run linear on this and see what ends up happening. So I don't see linear converging even. Let's give it up to 100 generations here. And I don't see, I don't see this happening with linear. Now I'm gonna pause it. Then what I'm gonna do is I'm gonna add in another hidden layer, and then so we've got now 3 hidden layers. We'll see if that changes anything. I suspect that this won't, because sometimes the math, in this case the linear activation, will only get you so far. And then you can't go any further than what the math allows for. So that's something that I don't think is going to work here. Now, with that said, I'm going to add in a couple more input features. So don't forget you've got these other input features here that give it some additional, the neural network, some additional patterns to work with. So I'm going to push play on this and see if we get any help, if this provides any extra help. And so far, it's wanting to. It's sort of kind of, you can see kind of some shades happening here. I'm going to stop. I'm going to add in a couple more. Let's just add all of them in. Let's add the sine waves in as well. So now what we're doing, so I'm going to restart that. All right, so linear works pretty quick if we give it some additional features. So that actually worked really well in classifying all of those. If we adjust not just the activation layer, but we adjust the input features. If we add another hidden layer, I don't think that's going to change anything. So let's push play on this and see what happens. It's still going to give us the same result. So there's a point of diminishing returns on something like this. Now, if we go to a simple classification exercise, which is bivariate. So in this case, I have 2 different clusters that are clearly delineated. Linear, regardless of what I send it, should be able to do this even like without any issue. So yeah, that's right. We don't have any issues. And I suspect that even if we back off some of the input features, let's go back to our base X1, X2 input features. There we go. And then we push play on this. It still gives us a nice clean delineation between cluster blue and cluster orange. And so, as a matter of fact, even if I back off the hidden layers, let's say I just go to two layers, and I push play, I should still get. And even if I did one, let's do one. Let's do this again and see what we get. It works great. So in terms of efficiency, linear activation on something like this that's a simple, easy cluster works great. So adding more layers on it doesn't do anything extra. So I'm going to push pause on this. And now one thing I want you to do, and this is for you to do afterwards, is try to figure out, I want you to play with this. I want you to look through the architectures that we look through in class or in our lecture. And then see, go ahead and add a bunch of different hidden layers. Then make them as big as you want. Put them in different shapes and sizes. You can put them in order as you saw in the lecture. There were like 6 of them, but there are 2 that you could actually recreate here, just based on the nodes by themselves. Some organizational patterns will work better than others. Additionally, some activation functions are going to work better than others as well. So what I want you to do is, as an example, I'm gonna pick linear, and just based on what I just added here, I'm gonna use linear to try to run this against the spiral. And you're going to see that it's not going to work really well. And linear right off the bat isn't going to help us because it's not converging properly, because it's wanting to do blue where there's orange, and it's wanting to do orange where there's blue. So what I want you to do, and this is for you to do on your own, is I want you to play around, and I want you to experiment with the neural network in this TensorFlow application, and see what, one, activation functions work better, and then what hidden layer structure did you have to create, and then 3, what features did you have to add to it to make this work, to where you could get a good classification. All right. And if you need inspiration in terms of what a good classification should look like, I gave you a picture of it in the lecture. So that's kind of what you're aiming for. Okay. With that, I hope that helped clear that up a little bit, based on, versus a video that wasn't moving too well for the last recording. I'm not sure what was going on with that, but hopefully this clears that up a bit, and we will see you in the next learning activity.